Hi, this is Dr. John Bergduff. In this video, we're going to look at properties of logarithms. Now, the properties you see on this slide are all incredibly important properties that you will be using in application problems as you go along. And there are videos coming up that describe situations where you can use each one of these properties. In this video, I want to first of all show them all to you, but I want to show you where they come from. So let's talk about them just very briefly, and then we'll look at the second part of what I want to do. So in all of the following, we're going to say that the m and the n both represent real numbers that are greater than 0. If you look where those are, these are quantities that you're substituting into the logarithmic functions. And recall that the domain of the basic logarithmic function with base a is 0 to infinity. So the only numbers you can substitute into a logarithmic function are positive numbers. The a in this is going to refer to the base, and like we've seen before, a has to be 0 and greater than 1. And there's also going to be in a couple of these properties a quantity r, and that can be any real number that you want. The first of the properties says that if you have a logarithm of a product, the logarithm of a product of two quantities, you can split that product into a sum of logarithms. Now, it probably would not be surprising that if you have a logarithm of an m times an n, you should be able to split that out somehow, but that it's the logarithm of the logarithm base a of m plus the logarithm base a of n, that's a bit surprising. The product splits up as a sum. Similarly, if 1 is believable, 2 probably would follow as believable, that if you have a logarithm of a quotient, that can split up into two logarithms as a subtraction. So if the first one is true, the second one seems plausible. The third one is my personal favorite. If you have a logarithm base a of a quantity to an exponent, that exponent can be essentially brought down up front as a coefficient and give you that r, that coefficient r, times the logarithm base a of m. This one's really useful. Also, there's a property about what the logarithm base a of 1 is. No matter what your base is, the logarithm of 1 is 0. And also, no matter whatever your base is, the logarithm base a of a is 1. And finally, an inverse relation that says, and this one looks complicated, but turns out to be just oh so easy, the logarithm base a of a to the r is the same as a raised to the logarithm base a of r, and both of those equal r. The r that's here and the r that's there. Now, again, in some future videos, there's going to be illustrations of how every one of these properties works and what you can do with them. What we're going to do in this video from this point on, however, is show where each one of these properties comes from. Now, you can work the problems in the book without seeing what I'm going to show you next. So think of what's going to come next as enrichment, so to speak, knowing the ideas, the rationale behind these ideas. So these are proofs. I doubt that anyone will call on you to reconstruct these on a test, but it can be very useful and give you some confidence in where these properties come from. We're going to look at them one at a time and illustrate, prove where they come from. So let's start with the product property that again says that the logarithm of a product of two quantities can be split up into a sum of logarithms. We want to prove why that works. And we're going to do that by recalling the basic definition of logarithmic notation, that an expression of this form is actually equivalent to an exponential form. This base raised to this exponent gives you this number. So the base a to the exponent y gives you the x. the quantity that's inside. Let's show how we can use that to illustrate that what is really going on here is that this property is a property of exponents in disguise. So here's what I'm going to do. I'm going to say let x equal the logarithm base a of m, and also let y be the logarithm base a of n. Now I'm going to use my definition of logarithmic notation to rewrite both of these statements in equivalent form. And don't worry too much that I've got x's and y's in different places. Think about the role of the base in the exponent. The statement I'm looking at first would say that this base raised to this exponent would give you this number. So this would translate to a to the x is equal to m. Similarly, this base raised to this exponent will give you this number. So this would translate to a to the y equal n. Now, let's look at m times n. That would be the same as saying a to the x times a to the y. Notice here I am multiplying two expressions, two exponential expressions with the same base. Now here's where you get the idea that the logarithmic property we're looking at is an exponential property in disguise. Because when we multiply two things with the same base, when you multiply with the same base, you add the exponents. Multiplications become additions. Hang on to that. That's the main point. So m times n is equal to a to the x plus y. Now, that's an exponential property. Let's take this and translate it back to logarithmic form. If I use my definition of logarithmic notation as a pattern, this x plus y is my exponent, so we would say that the exponent is the logarithm base a of the other side. X plus y equals log base a of m times n. Now, so what have I done? I've taken a logarithmic statement, unraveled it as an exponential statement, observed an exponential function, an exponential property rather, and translated it back. Now, x plus y, what was x? X was logarithm base a of m, and y was logarithm base a of n. So this illustrates that that sum corresponds to the logarithm of a product, or more cleanly stated, the logarithm of a product splits up as a sum of logarithms. Basically, it's this exponential property in disguise. Now, you may have to pause the video and watch this little part again, because this is quite elaborate for college algebra, but it's a wonderful way to prove that this property really is true. What about the quotient property? This is basically saying that the logarithm of a quotient splits up into a difference of logarithms. I'm going to prove this much the same way. I'm going to let, again, x equal logarithm base a of m. And again, then the base to the exponent is equal to the number, so it translates into exponential form like that. Also, y equal log base a of n, and that will translate into a to the y equal n. Then if you look at m divided by n, which would be a to the x divided by a to the y, we remember that when you divide two exponential expressions with the same base, you subtract the exponents. So divisions translate over to subtractions. And then if you take that and translate it back to logarithmic form, this would say, this would be my x minus y equals logarithm base A of m over n. And finally, replacing the x by logarithm base A of m and the y by logarithm base A of n, we see the exact property that the logarithm of a quotient splits up as a difference of logarithms. Now, the main thing you want to hang on to is that the property of logarithms we're looking at is really the property of exponents that you're seeing right here. In exponents, you divide two things with the same base. That division becomes a subtraction of exponents. The logarithm of a quotient becomes a subtraction of logarithms. It's the same thing, just in disguise. Again, you may need to pause the video, back it up, and watch this part again, because that's pretty elaborate. Now, the exponent property, the one that I said is my favorite property, is actually quite difficult to prove, a little bit beyond what we can do at this point. But it is pretty easy to give you, I think, a convincing demonstration of why this would work. Let's say, first of all, the r that represents the exponent here can be any real number. It can be an integer like a 2 or a 3. It could be the square root of 7. It could be anything you want. But let's illustrate this simply for the logarithm base A of m squared. So that's using 2 for r. Well, actually what you can do is you can remind yourself that the logarithm of m squared would be the logarithm of m times m. And from the addition property that we just looked at, or rather the product property that we just looked at, using m twice, this would be the same as logarithm base A of m plus logarithm base A of m. The product splits up into a sum of logarithms. And because these are like terms, we can rewrite that as 2 times logarithm base A of m. And so the way I like to visualize it is you can imagine that the exponent can be brought down up front as a coefficient. And so you have 2 logarithm base A of m. Logarithm of base A of m cubed would be logarithm base A of m plus logarithm base A of m plus logarithm base A of m 3 times. So that would be 3 times logarithm base A of m. Okay. Those are hard. This one is easy. Again, let's just, if you translate the expression that's given right here into exponential form, you'll see exactly why it works. Remember that we're saying that this base raised to this exponent is equal to this number. So this simply translates into a to the 0 equal 1. That's an exponential fact. This is a logarithmic fact. It's really the exponential fact in disguise. But very useful to remember that the logarithm base anything, it could be logarithm base 43, if you want to be crazy. The logarithm base 43 of 1 is 0. This next one, also very, very simple if you just translate it over. Again, a logarithmic statement looks a bit complicated, but it's simply saying that this base to this exponent equals this number. And that simply says that a to the 1 is equal to a, and that's true. So this is, again, a simple exponential statement in disguise. Of all the properties we have, this one looks probably the most intimidating. It's built on the concept of logarithmic functions and exponential functions being inverses of one another. So, for example, if you have the function f of x equal a to the x, basic exponential function, the inverse of that function is the logarithmic function. Now, there's a property that we saw way, way back when we looked first at inverses of functions that says if you take the composition of a function and its inverse, you'll always get x. Now in this case, the composition of the function and its inverse would be, again, like we've seen before, that's f of f inverse of x. F inverse of x is the logarithm base a of x. And then f of logarithm base a of x would tell me to go back to the definition of the function f, and where I see the x, replace it by whatever is inside these parentheses. So that would give me the very complicated looking expression a times logarithm base a of x. But if when you do that composition, you're supposed to get x, this is really just saying a to the logarithm base a of x would be x. The composition just gives you x. And the only thing that's different about the statement of the way I stated it up here in the theorem is simply I used r instead of x. So the other one works exactly the same way. If I can kind of clean up some space here for a second. It is also supposed to be true that the inverse taken in the other order should also give you x. F inverse of f of x should also be x. F inverse of f of x would be f inverse of f of x, or f inverse of a to the x, and that would be logarithm base a of a to the x. And because that composition is supposed to give me x, that tells me that this is indeed equal to x. And again, in my statement, I just replaced the x with r. So this rather complicated looking relationship is built on the fact that the exponential function with base a and the logarithmic function with base a are inverses of each other. Now in the upcoming videos, there's not going to be an example that illustrates this inverse relation, so I want to go ahead and put one of those in here real quick. We're going to solve this equation. It looks absolutely intimidating, but if you think about the fact that in this case 5 raised to the log base 5 of something r would just be r, then this expression on the left basically says that the function in the inverse composed to give you just what is inside the function. So the expression on the left side of this really simplifies down to nothing more than 2x plus 3. So really all you're being asked to do is solve 2x plus 3 equals 7. That's using that logarithmic notation. All right. Now, can we solve 2x plus 3 equals 7? Yeah, I think so. Subtract 3 from both sides, 2x equals 4, divide by 2, x is equal to 2, and my solution set contains 2. So again, this is sort of a theoretical video. You can work the problems in this section as long as you know the properties. If mainly think of this as you've had an opportunity to see where these properties come from. Even if you can't recreate these proofs for yourself, it gives you that confidence that all logarithmic properties are really exponential properties that have been disguised, plus the idea of inverses. So I hope that helps, and in the next videos you'll see some nice applications.